Alright, welcome to another AQA AS chemistry video. Today I'm going to be doing a video on calorimetry. This video is called calorimetry. Is quite a big, I say big topic, but it's quite a big topic for physical chemistry in particular because it's a practical kind of relates to some of the topics in year 2, but it's mostly just a good practical that relates to calculating enthalpy changes realistically. So, and it's the only real. I mean, there are other examples, but calorimetry is the only example that you need to know, at least at the AS chemistry, for calculating enthalpy changes or bond enthalpy. And yeah, I'm going to be going through the video. I'm going to be going through what calorimetry is. I'm not going through the practical. I'm not going to go through the practical. That's probably something that your teacher will go through much better than I would. In case people really want that, I can make the video. But I'm going through the different types of calorimetry, and more importantly, the calculations. That calculations are the ones that so it's quite common. They're not difficult, but it's quite big in the sense that it comes up quite often in an exam, and it used to be generally quite a lot of marks. So I'm going to be going through that today. Alright, so let's go for it. So calorimetry is used to physically measure changes in energy. Bomb calorimetry. So bomb calorimetry uses a machine called a bomb calorimeter to measure the enthalpy changes of combustion, and this process involves burning a sample of a compound in a sealed vessel and measuring the temperature change. So this temperature change here, right? Sorry, on 9 actually. There you go. Temperature change is quite important when it comes to that's one of the big things you need to understand for bomb calorimetry because you have a sealed vessel, burning a sample. You want the energy because I'm going to go through why this temperature change is important. It's kind of related to the equation thing, but I'll show you the equation later on when we get to it. But one of the things is to get the temperature change, and it allows you to, if you have the temperature change, you can substitute that into your equation that I will go through later on, and then you can work out the enthalpy. And then once you have the enthalpy and you get the moles of your reaction, you can work out the enthalpy change. As I said, I'll go through that, but temperature, the main thing of calorimetry experiments is temperature change. That's what you can use to work out the enthalpy. Right. So combustion reactions burn a chemical in a calorimeter, and we measure the temperature change of the surrounding volume of water to determine the enthalpy change. I say water. I don't think they ever ask it, but in case they ever do, the reason why we use water, as you remember from GCSE, water's got a very high specific heat capacity, and it's very good at equally distributing that heat. So it just makes sure that the entire compound, with the thing that you're heating, is being equally heated on all surfaces, and on all places at the same time. So that's the reason why we use whereas if you have other compounds, they might have hotspots, which are just areas or regions where it gets hotter rather than on the sides, and that's what we want to avoid that, because that could cause incomplete combustion or an incomplete reaction at least. Alrighty then. Right. Often the calorimeter will just determine the temperature change in the vessel, and you have to calculate the enthalpy change of combustion. Yeah, it would be incomplete combustion. Yeah, sorry, I was getting wrong. But it would be incomplete combustion. Right, so often the calorimeter will just determine the temperature change in the vessel, and you have to calculate the enthalpy change of a combustion. Right. So I'm gonna go through this. This is what a bomb calorimeter looks like. Don't ask you why it's called a bomb calorimeter. I don't know for certain if this is what they used for bombs. It would make sense if it was though, but I'm not gonna assume. But this is what it looks like. You don't actually need to know this what it looks like, but in case you see it in an exam, you don't get shocked and like, what the hell is that? It's just this is what a bomb calorimeter looks like. They obviously cut this part open so you can see what's inside. Yeah, water to equally distribute the heat that's around there. Sealed vessel, O2 intake. In university, they use magnetic spinners or magnetic stirrers or motorized stirrers instead of using a glass rod, because if you use a glass rod to stir, some of your product is going to end up on your glass rod, and that can make your reactions cause inaccuracies in your calculation. So that's it. But you don't need to know what this looks like, but just need to understand what it is in case you ever see it in the exam. That's one way. But there are inaccuracies in bomb calorimetry. So bomb calorimetry can be inaccurate due to heat loss to the surroundings and any incomplete combustion that may take place, and then maybe a loss of some reactants that evaporate before it combusts. So even before you start a reaction, there may be actually a loss. So you have to basically you start your reaction as quickly as possible as soon as you pour your compound in. So these three things here, I know it doesn't sound as important, but these are the type of things that they ask you in your exam, and they're easy marks. So if they ever ask why the reaction didn't go to completion or why the results were different to this reaction, it's because of the inaccuracies in an experiment. Heat loss to the surroundings. You should know that from physics, really GCSE. Any incomplete reaction that may have taken place, we discussed this when I did the percentage yield topic, and most of these kind of relate to kind of the percentage yield topic. I can go back to my video on percentage yield, and if you want to, I mean, I could leave the link in the description, I guess, for that for percentage yield. But yeah, loss of some reactants that evaporated before it combusts again. If you need more examples, if you go to my percentage yield video or percentage yield slash atom economy video, those are different inaccuracies. These are just practical things that can happen, right? So calculating enthalpy change. So I'm going to go through that now. So calculating enthalpy changes. The equation to calculate enthalpy change from temperature change is similar to the one that you remember from GCSE when it comes to the specific heat capacity. In physics, it's usually E equals mc delta T, but it's just Q. Q and E really they represent the same thing. They're representing energy. Q here represents the heat energy or internal energy. When we're saying delta, but now when we're talking about delta E or enthalpy change or E in chemistry, we're talking about enthalpy. And that's slightly different to energy. I went through that in my previous video, describing energy and enthalpy. Check that out. Would I leave a link in the description? I probably would leave a link in the description, but in case I didn't, it's just my previous video. Alright, so Q is equal to mc delta T. I'm going to try and talk, I don't want to talk too much in the video, but forgive me if I have. So Q is the heat energy, M is the mass of the sample, C is the specific heat capacity, and delta T is the temperature change. And then this is what we get this value from our experiment. C is just the specific heat capacity of water, so it's usually 4.18. The mass of the sample, that mass is, don't get confused with this one, right? Don't get confused. Don't think this is the mass of the sample of the compound that we're measuring. No, it's the mass of the water. When you're working out, this is all of this is the mass of or related to water. So the mass of the water, specific heat capacity of water, and the temperature change of water. And then when you're working out the moles, you use the mass. You could obviously use moles is equal to the mass of the MR. Use the mass of the compound. So if you're trying to work out the specific heat capacity, so if you're not specific capacity, if you're trying to work out the enthalpy change of, let's say, potassium chloride, right, and they give you 5 grams of potassium chloride, and you're using a sample of, let's say, 100 grams, 100 milliliters of water. Let's say 100 milliliters of water, but you know that the density of water is 1, so just 1 milliliter is equal to 1 gram, right? So when you're doing this part, be Q is equal to 100 times by the C of 4.18 times by the change in temperature that you would have measured, and then your moles would be your mass of your potassium chloride, which is 5 grams in this case, over the MR. I forgot what would that be now? 39 plus 36, 35.5. In case if that's wrong, then forgive me. But the point is, I don't get confused between this mass, which is the mass of water, and the mass of your compound, right? So if the pressure is constant, Q is equal to delta CH. If the pressure is constant, of course. All right, calculating enthalpy changes. We've calculated Q with the energy given off of the surroundings, which is enthalpy change, and the unit of Q is in joules. As I said before, Q can be just represented by E, but it's not to get confused in chemistry when we say E or energy, we're referring to the enthalpy. It's actually the enthalpy, but Q is just energy. It's just the energy in joules. To determine the enthalpy of combustion, we must convert joules into the units of enthalpy change, which is joules per mole, or kilojoules per mole, but joules energy per moles, right? Calculate the number of moles equals the mass of the MR, and then the delta H, right? Delta H is that, right? So delta H, we've worked out Q, worked out the moles. Delta H, if you can see simply from the units, but it's kilojoules, it's joules per mole, right? You usually use kilojoules, but joules per mole. Therefore, it's our energy in joules over our value in moles, and that is your enthalpy change. So more calorimetry. So calorimetry is a very useful technique to determine the enthalpy changes. Different types of calorimetry. Calorimetry can also be used to measure other enthalpy changes. we've considered the combustion reaction that gives off heat, but there are other examples of calorimetry. We can also measure any reaction that can be done in a sealed vessel. For example, you can measure the enthalpy change of a neutralization of an acid-base reaction. So this is the one that you usually do in your I mean, I think you do both, definitely not bomb calorimetry. No, you could do that one. You could no, you could definitely do there's two types of calorimetry that you do, right? You do the neutralization calorimetry, and you do the combustion calorimetry, or I guess it'd be the bomb calorimetry. For A, but that's the one at least I did for AQA. These are all AQA. I put in the title, but for AQA, those are two that you'll do with your teacher. So accurate temperature changes. So you might think that the best measurements to record are the initial and final temperature, and this is quite important, right? So you, in your head, you're thinking, if I want to measure the temperature change, I'll just measure the initial and the final temperature of your calorimeter. But this isn't the case because heat is always being lost from the calorimeter. So the final and initial temperature can actually be inaccurate, and you'll see it here, right? So instead of measuring the temperature loss of the reaction, after the reaction is complete, you would extrapolate a line to find the true value. So this is, I'll show you what I mean here, right? So if I was to do, let's say that we start off our compound here, right? We would have our calorimeter, which is our water, right? And then it's just hot water. We haven't added our compound in, right? After, I can see here from roughly 1.5 minutes, they've added our compound in. And then once they've added the compound in, it's extremely exothermic reaction because bonds are being formed. So lots of heat energy is being released to the water. And there's a gradual increase. You can say gradual. It's quite I wouldn't say gradual. I say it's a spike. Over time it will feel like a gradual increase, but in terms of when you're looking or describing this graph, you say it's generally a spike in the temperature, all the way up till what's this now, 26, 27, 27.8, right? And then once it reaches the peak, then it kind of gradually that's the gradual decrease, right? And from this is the part that we care about, because that's the actual that's after the reaction's now happened, and now all the reactions still occurring, but it's after our compound's been added, and now we can see this kind of gradual line here. We would extrapolate this line. What extrapolating actually means is that we run off. So this is clearly our line of best fit, and then we continue all the way back until the time that we added our compound in, which is minutes. 1.5. I say 1.5, and that's our actual that's our actual initial temperature. That's our actual initial temperature of the reaction. Or some heat would have been lost between here and here, but the initial temperature or initial temperature of the reaction would have been, what's that now? That's 29. So it's 28.5 degrees. So that's how you work out your initial temperature, right? Or actually, no. It would be, yeah. That's your initial temperature. And you're measuring temperature change, right? Initial final temperature. This temperature here minus this initial temperature. That's your temperature change. The difference between here to here, that's your temperature change. That's the one that you would measure. Your initial temperature minus this extrapolated temperature here. That's your initial temperature. That's the one that you would use, and that's what you're trying to gain from this reaction. You're trying to gain this line, and then hopefully you get. I've said this like 6 times now, but you get what I'm trying to say. All right, so I'm gonna go through some example calculations. Calorimetry experiment. So combustion of cyclohexane. So I'm going to go through a couple of examples. So cyclohexane fuel is burned completely in a calorimeter. There are 200 grams of water in the calorimeter. There are half a mole of cyclohexane burnt. The temperature of water was raised from 298 Kelvin to 368 Kelvin. All right, the calculation. So I'll go through it here, but first I want to say that cyclohexane is extremely difficult to get a complete. If we're going back by the enthalpy of combustion definition here, right, is complete combustion, a plentiful supply of oxygen. It's quite hard to get complete combustion of cyclohexane simply because there's a lot of carbon density, so it's actually quite hard, but it is possible, right? So, and they've already worked out the moles for you. They've given you the mass, so if they want you to work out the calculation, right? So if they want you to work out the, if you want to work out Q, if you want to work out the enthalpy change of this reaction, we work out Q, right? So Q will be equal to MC delta T, as we know here. The mass of the water, which is 200 grams, times by the specific heat capacity of water, which is 4.18 joules per gram per Kelvin, and then times by the temperature change, which is 70, which is 368 minus 298, which is 70. The Q is equal to 58,520 joules. And then if you want to look at the enthalpy change of combustion is equal to Q over the moles. So it's actually minus 58,520, because remember, this is an exothermic reaction. Energy is being lost to the surroundings, so it's losing that energy. So it's minus 58,520 over our moles, which is 0.5 or half a mole. Yeah, remember, the water temperature being increased, and that's being heated. It's heating the water when it's happened. So that's why it's minus. It's always a negative. Alright, once you do that part, delta H is equal to minus 117,040 joules per mole. And in the reaction, usually when we do in chemistry, it's kilojoules per mole. That's the one that we use. In the exam, unless they specifically specify and you left it as that, you wouldn't lose the mark, because it's still in the form of joules, energy per mole, or joules per mole. But usually in the reaction, they'll say it, and usually just another mark gained for just showing that you answered, you read the question where it says kilojoules per mole, and that's just by dividing it by 1,000. So it'll be minus 117.04. And if we want it to three significant figures, or we can see it's three significant figures, like in this question here, they've used three significant figures. It should be it will be 0.500. Sorry, I copied it wrong, but we just leave it as minus 117 kilojoules per mole. And it's an extra mark for mentioning that it's a minus, because obviously it's an exothermic reaction. Right, so yeah, go through this. Okay, here's another question for you now. Pause the video now and try and answer the question. So 0.05 kilograms of cyclohexene is burnt completely and heats surrounding water by 100 Kelvin. Calculate the internal energy of the reaction. Pause the video now and try and answer the question. Oh. Alright, I'll assume you've paused the video and tried to answer the question, and I'll go through it. I think I did try to answer the question before, but I can just show you exactly what I did from the scraps. Is this it? Okay, good. I'll go through it now. So, working out, they want us to work out the internal energy of the reaction. So, Q is equal to MC delta T. We have the mass of cyclohexene burnt. Q 500 is the same as 0.05, right? If we get the mass here, right? 0.05 times by 1,000. Remember, we use grams in chemistry, and that's just 50 grams. So Q is equal to 50 times by 4.18 times by the temperature change, which is 100. Get my calculator out somewhere. I should have prepared this before I did my video. There it is. Yeah. 20,900. Sorry for that delay. I left my calculator somewhere else, but 20,900 joules. And that's it. That's all it is. I'm going to go through now a couple questions. I won't do all of them, but I'll do some of them. So, that business is done now. Great. So I get my pen. Right, so try and answer these questions. So it's going to be from do all the way from question 1 all the way up until, that's question here, this question here, all the way up to question 2. I'll do the rest of the video, I'll do the rest of the questions later on, but it should take you 17 minutes, 17 questions, 17 minutes to try and do these questions. I'll go through the rest of the questions later on. I got this in physics and maths tutor. Yeah, so yeah, should be able to do this. Alright, pause the video now, try and answer the questions. Alright, I'm going to assume that you've already tried to answer questions. So I'm going to try and do this in 17 minutes to show you how I would do it, or if you really need to go get the mark scheme, you can just go use the mark scheme from physics and maths tutor. But I will go and try and explain to you in case you got stuck. Good, 17-minute timer. So, propanol can be formed when glucose comes into contact with the bacteria in the absence of air. Balance the following equation for the first reaction of glucose to form propanol, carbon dioxide, and water. So how would I go about this? So carbon, hydrogen, oxygen, carbon, hydrogen, oxygen, 6, 12, 6. Carbon here, 1, 2, 3, 4. Hydrogen is 8. Oxygen is 4. Alright, so 1 plus, I'll probably start here. If I increase that by 2b, that's 6 carbons, 7. And that's just not going to work, is it? Because if I make that to 7, it needs to have okay. You have to play around with these questions sometimes. If I make that to 8, well, that means I have to do this to this 2 as well. So 2, and then that will become 12. Just trying to balance the carbons first. 12. If I make that 3, that's 9. And they'll both be 12. So I could just go 3 here, 3 here, and that makes that 12. Oh, that makes that 12. Now if I do that, so that's 24 now. That's 12 as well. So 6, 12, 18. That's 18. Oxygen is 3. So that's 6, 9. And if I just make that into a, if I just make that 3, and then that'll be 6 times by 2, that's 6. That means that would be, that's not plus 6, that's 24, 24, which is good. 12, 24. And then that would be also 12. Yes, yeah. So that's it, right? 2, 3, 3, 3. And that's it, that's balanced there. Deduce the role of bacteria in this reaction. Probably not going to be using, can be formed when glucose comes into contact with bacteria. No, I say acts as a catalyst, or it speeds up the reaction. So acts as a catalyst. If bacteria is not getting used up, it acts as a catalyst because bacteria isn't getting used up. So propanol is also formed by the oxidation of propan-2-ol. Write an equation for this reaction using the O to represent the oxidizing agent. Write an equation for this reaction using H3C CHOH CH3 propanol is just CH3 CO CH3, and then be plus a H2O, right? Because you have H2O. CHO 3 8 2 3 8. Yeah, that's balanced already. I say the class of alcohol to which propanol belongs to secondary alcohol. Right. A student determined the value of the enthalpy change when the sample of propanone was burned. The heat produced was used to warm some water in a copper calorimeter. The student found the temperature of 150 grams of water increased by 8 degrees when 4.50 times 10 to the power minus 3 moles of pure propanol was burned in air. Use the student's results to calculate the value in kilojoules per mole for enthalpy change. When 1 mole of propanol is burned, the specific heat capacity of water is 4.18 joules per Kelvin per gram. Alright, so they've given you this, so you already know. The first thing I'd write down is this. Always write down your equation. You won't always get a mark for your equations, but at least you know where to start. They've already given you the moles. Q is equal to delta H is equal to Q over moles, just showing that where you want to go. Gives you a blueprint of what you want to do. First of all, we're given the mass, the specific heat capacity we have, and temperature change we already have. So mass of the water is 150 grams. 150 times by 4.18 multiplied by 8. Q is equal to 5,016 joules. Is what I've been given. So 150 times by 4.18. Yep. And then sorry, let's make sure that wasn't wrong. And delta H would be equal to 5,016 over our moles, which is 4.50 times 10 to the power of minus 3. Delta H is equal to 4.5 times 10 to the power of minus 3. 1,114,666.667 current, but I'll leave that part. I just leave it as 0.7, right? Joules per mole. They want it in kilojoules per mole. Divide that by 1,000. So the delta is a 1. Delta H is equal to, I know it's pretty obvious here, but it's just like showing it. They really want you to show it, that you understand. So I'll leave this actually. I remember this is a negative reaction, right? So it'll be actually, Q is actually minus 5,016. Minus 1,115 kilojoules per mole. How much time have we got now? 9 minutes to do the rest of this. Define standard enthalpy of combustion is this on the screen, right? Yeah. So let me just make sure. Can everyone see that part? In case they didn't see that part there. Okay, good. My camera's kind of put in an awkward position, so I can't really see what you're seeing. But hopefully you got that part. Define the term standard enthalpy of combustion is the enthalpy change. Remember, these definitions are quite important because they will just ask you straight, well, what's the definition of this? The enthalpy change when 1 mole of a substance is burned completely in an excess of oxygen and also and all reactants are in the standard state. Alright, use the mean bond entities data in the table and the equation given below the table to calculate a value for the standard enthalpy of change when gaseous propanol is burned. So this is going to be, remember, this is bond enthalpies is not products versus reactions. It's actually reactants. When you're doing the enthalpy, bond enthalpy is actually reactants minus the products. So reactants, you get a mark for this, or saying something more or less on the same lines as this, minus the products. Delta H equal to so we want us to bond enthalpy. We want us to get the mean bond enthalpy, standard enthalpy change. Okay. 6 by 412 plus 2 by 348. Usually you draw it out, but just for the sake of time, I've decided not to draw. I can just see what the bonds are. If you really struggle with this question, I can go on over that later at the end. But just for the sake of time, I decided to just go and do that instead. Carbon-oxygen bond is this how, sorry, plus 805 plus 4 by 496 minus this, which is 6 by 805 plus 6 by 463. Delta H, work out the first part. Five nine five seven minus 7608. Just make sure that's right. Alright, and then just taking away these part, and then you should get, so 5957 minus answer minus 1651 kilojoules per mole. That's it. Suggest 2 reasons why the value obtained by the student in part C is different from the value calculated in part E. So first, value about, because heat can be, so first thing I'll talk about is that heat can be lost to surroundings. I say heat, if it's one's an experimental value, so heat can be lost to surroundings. Yeah. Keep messing this up. I mean, it's just changes. Yeah, it's just changes in your it just changes. It's just to do one is experimental value, one is a mean bond enthalpy value. So it's a calculation. So the difference is just the fact that one can be in an experiment, he can be lost to the surroundings, causing inaccuracies. Another one, well, if it's an experimental, there could be some incomplete combustion, I think. So there can be some incomplete combustion. Forgive me, I haven't done this topic in quite a long time, so this is just straight off my head. So there could be some incomplete combustion. Yeah, last one. 2 minutes left for the last one. So, a value for enthalpy of combustion of an alcohol can be determined using the apparatus shown in the diagram below. The calorimeter is held by a position with the clamp. So this is how actually one of your calorimetry experiments will look like. You'll do it. You have a spirit burn of an alcohol, measure the change in mass of the alcohol. But anyway, here to the question. This experiment can be repeated by using a different volume of water that would result in a more accurate value for the enthalpy of combustion because there would be a reduction in the heat loss. Okay, so you can change this. Okay, so state a change in the volume of water that would cause a reduction in heat loss and explain your answer. Oh, just increase it. Just increase the volume. Because you're increasing the contact between the water and the calorimeter. Increase, yeah, increasing or increase the. There's an can I go to this? There's an increase. One minute 10. There's an increase in the contact between the water and calorimeter. Alright, and that's it. There's now 45 seconds left on the clock. This is where you go back, and I'm gonna go try and explain this. I'll do the rest of the questions on a separate video. Don't worry, I just said to go up to question 2. I'll go through the mark scheme. That's how I'll do these questions. You can go. I'll leave a link in the description to the mark scheme. You can, if you need to compare. I don't know if these these answers are correct, but this is how I would go through them. Yeah. I'll do the rest of the video, and then at the end of completing the rest of the video, I'll go and mark the rest of the questions. And yeah, that's it.